So far we've seen and talked about the fact that energy cannot be created or destroyed when it changes from one form to another, but we'll often hear people talk about energy being lost. And lost really just means that the energy's been converted into some form that we didn't actually need or can't be converted into any other forms easily. And this is occurring anytime something does some negative work on the original system. So for example, when we were dealing with gravitational and kinetic energy, we started with simple examples. So maybe something like a skydiver jumping out of an airplane. And up until now, we've focused on just the skydiver itself falling through the air. And so we'd really just talk about their gravitational energy and their kinetic energy that they converted into. But what we can also now talk about is the fact that air resistance will be a factor as well. So the air particles are going to push back against the person, and that's actually going to take away some of their energy. In other words, that air is doing negative work on the original system, which was the skydiver. It's also possible that maybe the skydiver could be wearing a jetpack, and they might have something that could do positive work. So maybe their jetpack could actually kick in and cause them to accelerate quicker towards the ground than they would if they were just falling. So that jetpack would be actually doing positive work, adding more energy to the original system that wasn't there before. So to account for all this, we're just going to correct our formula a little bit and add an extra term to it. Specifically, we're going to add W, some extra work that's being done by something else that wasn't in our original system that we were discussing. So that could take on two different possible forms. If something is doing positive work on the system, like our jetpack, then that W value is positive as well, and our total final energy is actually greater than our initial energy. But if we're dealing with something that's doing negative work, which we might call energy lost, then that W or work value is actually negative. So that would be like the air resistance would be doing negative work, and in that case our total final energy is less than our initial energy. So even though we could technically have some cases where we have positive work being done, we're mainly going to focus for the rest of these examples and in most of your hit list questions on the case where energy is lost, because that's the more common thing that we deal with in engineering applications. Even if we take an example we've seen before, we can think about how energy would be lost. So we talked about the pendulum in our previous note, and we talked about how theoretically the pendulum should always rise to the same level that it started from as it swings back and forth. But in reality it doesn't, because there will be some energy lost due to some air resistance. Once again, as the bob flies through the air, it'll feel air resistance, slowing it down a little bit. And there's also a little bit of friction at the fulcrum point where our swinging arm is actually attached. And so that friction as well is something that will take away some of the original energy. And that energy didn't completely disappear. It's actually going into slightly raising the temperatures of the air around it or of the fulcrum itself. So that frictional energy or air resistance energy is really just being converted into thermal energy. In general, though, from now on, when you're solving problems, never assume that energy is being lost or that any new energy is being given from some other source. Only include this assumption if it specifically says so in the question. So in general, if it doesn't say anything about energy being lost or extra energy being gained, just assume that it's a regular conservation of energy question like we dealt with in note 4. But if we are told that some energy is lost, how can we use our new formula to actually solve it? That's where we want to go from here. So we'll start with an example that's very similar to the ones that we would have dealt with in note 4, but has an extra little wrinkle added to it. So we've got a 2.4 kilogram block that slides from rest down a 6.2 meter high ramp. But now we also know that 52 joules of energy are being lost because of the frictional heat created as it slides down the ramp. So we want to know its final speed now. And there's a follow-up to this where we could also try and find its final speed if the ramp was totally frictionless, so if no energy had been lost. But that second part I'm actually going to leave for you to try afterwards. We're just going to deal with this first part that involves what do we do with this frictional heat being lost. So we'll set up an initial and final chart to start with, just like we did in our previous note. So remember H1, M, and V1, H2, M, and V2. And for our heights, well, we could say that our zero line could be at the very bottom of the ramp. So when we finally get to the bottom of the ramp, we'll be at 0 meters above our initial zero line. which means at the very top of the ramp we are 6.2 meters in the air above that zero line. We can make note of the mass, which I know in some calculations actually isn't important, but we're going to see that it will be in this case, so we'll write down that it's 2.4 kilograms, and keep in mind that it will still be 2.4 kilograms as it gets to the bottom, because we're going to assume that it didn't go through some kind of weight loss program on its way from the top of the ramp to the bottom. Its initial velocity isn't directly stated in number form, but it does say it starts from rest. So that's telling you it started at 0 meters per second, and we're trying to find that final velocity, so that's v2 is actually our question mark there. That's our required value. One other piece of information, though, that we don't need to actually include in our initial final chart, but we should still state, is that work value for the frictional heat. And remember that it is work. It's work being done by the friction in the actual ramp that it's sliding down. And so I'll write down that that's 52 joules, but I'm going to be a bit more careful as I do that. Because if I look at the question really carefully, I'll remember that it's 52 joules of energy that's being lost. And that means it's actually decreasing the original energy that I had in total. So when I plug this in, I actually am going to plug it in as negative 52 joules because the energy is being lost. If this was some new energy that was being gained, maybe if somebody gave this block an extra push down the ramp, then that would be positive work being done, and I would plug in a positive value for W. In this case, though, it's energy being lost or taken away, and so when I add that work value in, I'll actually be adding a negative, which is what's actually going to take away those joules of energy. So now we have everything we need to jump right into a solution. We just need to make sure we rely on our new formula. So instead of just saying that total energy initially is completely equal to our final total energy, we're going to add in that extra work value. So that's what our new version of the formula really says. I can replace those then with some specific formulas to represent them. So that would be like mgh1 plus 1/2 mv1 squared. So I'm just jumping right into the gravitational and kinetic energy formulas, which is okay in this case. But then remember, I still have some additional work value that we'll plug in later on, and then I have my final values after. So mgh2 plus 1/2 mv2 squared. Now in previous questions, in our previous note, this would often be the step where you might want to try and cancel out mass from every term. Except the problem is, in this case, mass is not required in every term. It's actually not used at all in this particular term here. That's just a W, and it doesn't depend on mass at all. So in that case, we can't actually cancel mass out because it doesn't divide evenly out of every single term. So in this case, we're going to have to leave the mass in. But there is some other simplifying we can do. So remember that H2 is 0 meters. So any term that involves H2 is going to go to 0 and completely disappear from our calculation. We also know that V1, or the initial velocity, was 0, so anything that involves V1 is going to get eliminated from our calculations as well. And that just makes it a little bit simpler when we actually go to start substituting some things in. So in reality then, that means we have mgh1 plus W equals 1/2 mv2 squared. From there, I can just plug in the things that I know. So that's 2.4 for the mass, 9.8 for the acceleration due to gravity, and 6.2 is the height that we're starting from. And now I need to be really careful. I'm going to add negative 52 joules. Or if you wanted to, you could just think of that as subtracting 52 joules. I'd be okay if you just wrote it that way, but I'm just going to remind you that we are adding some work that's being done, but it's a negative form of work. Work that is taking away from the initial energy that we have. And that's all equal to 1/2 times 2.4 times V2, which is what we're looking at, squared. If I simplify and bunch together all of the things I have on the left side of the equation, that gives me 93.8. On the other side then, if I multiply 1/2 times 2.4, I get 1.2, and then I still have my variable V2 being squared attached to that. So I can take another step and divide both sides by 1.2. I'm going to write mine to the side now. So when I divide both sides by 1.2, that tells me that 78.2 is equal to V2 squared. So that's telling me that V2 on its own, when I square root 78.2, is approximately equal to 8.8 meters per second. And of course, then you'd finish it off with a therefore statement that says, therefore, at the bottom of the ramp, that block would be going at 8.8 meters per second. I want you to try and do the follow-up to that, which is to say, what would the block be doing if there was no frictional heat lost at all? So in other words, if this was a totally frictionless ramp, and it was more similar to the questions that we did in note 4, what would the new velocity be? And in this case, what you should find for the new final speed, and you can use this as a way to check, so V2 in this case should be approximately 11 meters per second. So take some time and try that, and see if the new final speed when you try it without that heat being lost is actually 11 meters per second, and it's just a little bit of extra practice in the skills that we learned in our previous note. Example 2 requires a little bit of extra calculation because the amount of work being lost is not directly given to you. So we'll save that one for class and go over some of these things first, and then see how we can add a little calculation in to figure out how much work is being done and how that's going to affect our final speed.